Hello everyone, and welcome to the dry ice puck on a ramp post-lab extension. So this rather long process here has brought us to one more graph to analyze and to try to understand all the properties of, which is a graph of velocity versus time. And we had to do some tricky things with graphical analysis to find a bunch of slopes of the tangent lines to the position time graph, the velocities, so that we could make this velocity versus time graph. And when you got around to graphing your velocity in centimeters per second versus your time in seconds, your graph hopefully looked pretty much like this. A nice linear graph that went through 0, 0. And as we well know by now in physics, when you graph two variables and they result in a graph which is both linear and goes through 0, 0, we can say that those variables are proportional to one another. And certainly if you're looking at your lab sheet right now, your lab extension sheet I should say, which you should have in front of you so that you can take notes on it and check your results and all of that. Right? But if you should be able to see this in the data, right? If you take a time and then double that time, you get twice as fast. Triple the time, you get 3 times as fast. It's a direct proportion. Came from a little more complex position versus time squared, or position, proportional to time squared, right, results, but this gave us a diagonal line velocity time graph. So a changing velocity. Well, let's create a math model of this linear graph using our old friend y equals mx plus b. Y, in this case, would be what we graph on the vertical axis, which is velocity, which we would call a v, with an arrow, it's a vector. And that equals your slope. Now, I'm assuming that if your slope worked in the Google form and everything, you should have a slope of somewhere around 356, give or take a few percent. Right? Give or take 5 or so, one way or the other. Seemed like that was working for people. After all, we are analyzing a video in this case, so we don't have real life getting in the way. And one of the fundamental questions of this whole lab and lab extension cycle that we've been working on is what the heck does this slope mean? What does it tell us about the motion of your dry ice puck as it moves down the ramp? Well, to analyze that, we really need some units to give some context. How do we find units for slope? Same way we find slope, rise over run. So our units of rise are centimeters per second, and our units of run are seconds. Now, we could reduce these units, and we will in a few minutes, but it's easier to interpret the meaning if you leave the units kind of this way for now. Okay, so centimeters per second per second. So what does this slope actually mean? What does it tell you about the motion of your dry ice puck? I want you to write a for every statement for this using your number. Now, you don't have to use my slope number, 356. You can use yours. It should be pretty close to this. Well, let me try to help you out a little bit here. Right, how many points does it take to find a slope? 2. How do you find a slope between 2 points? Rise over run. Since this is a graph of velocity versus time, the rise tells us how much the velocity changes between these 2 points, right? How much the velocity changes, and the run tells us how much the time changes. Slopes are rates of change. They tell us how much one variable changes when you change the other variable. Right, so can we put this into a for every statement? For every 1 second of time, the velocity increases by 356 centimeters per second. So for every second, the puck's velocity increased 356 centimeters per second. Now, this is a fairly complex little idea here. All right? It's not telling you how fast the puck is moving, which is its velocity. It's telling you how fast it's getting faster. Right? It's getting faster by 356 centimeters per second every second. Right? So this is a little different of a quantity, but it is a quantity that you know, or at least you might have thought you knew, though maybe not to the depth that it really exists, as we found many things in physics to be a little deeper than in common English. But anybody know what we call this quantity? Yeah, it's known as acceleration. denoted in an equation by a lowercase a with an arrow because it is a vector, although the vector part of it is a little complex, but we'll do a whole activity to figure out that. Okay. So we're going to define the acceleration operationally to be the slope of a velocity time graph. Now we could turn this into words, right? Slope is rise over run, and the rise is the change in the velocity, and the run is the change in the time. So in symbols, this little statement, definition if you will, can be written this way. The acceleration is change in velocity over change in time. Or in kind of more concise math language, it's the rate of change of velocity. So we can see already why acceleration is a complex little thing for us to figure out, okay? Because it's the rate of change of a rate of change, right? Velocity is already the rate of change of position, how quickly your position's changing, so many centimeters every second. Now acceleration is how quickly that velocity is changing, speeding up, slowing down, changing direction. Right? Anything that changes the velocity means that it's accelerating. So this is a term that we use a lot, but not everybody really knows exactly what it means. They often confuse it with velocity. Something could be going very fast, but have virtually no acceleration. Right? If a car is driving 75 miles an hour down the highway, but it isn't speeding up or slowing down, it's got an acceleration of 0. Right? There is no rate of change of velocity. The velocity time graph would be a horizontal line at 75 miles an hour. On the other hand, something could be going very slowly, yet speeding up very quickly, yet accelerating very quickly. Right? If you spin the wheels on your car and take off, you're not moving very fast at the beginning, but you are speeding up very quickly. So we're going to work for several more weeks here on this concept of acceleration and what it tells us about motion, and combining it together with the ideas we know of position and velocity. We're even going to make a graph for it eventually. So let's finish our math model. First off, let's take a look at these units. We have centimeters per second per second. Well, what's that horizontal line actually mean? It means divide. So this is a centimeter per second divided by a second. And dividing by something is the same as multiplying by its reciprocal. The reciprocal of seconds, which is really seconds over 1, right, is 1 over a second. With me there? So dividing by a second is multiplying by 1 over a second. And so a centimeter per second divided by a second is a centimeter per second times 1 over a second, which is a centimeter per second squared. Now, notice, if you write the units this way, which we traditionally do, right, it's kind of hard to figure out what it means, right, because it's kind of hidden in there. This is really what you got to think about, which is why we start with a graph, right, to look at the velocity time graph. So if you're trying to interpret an acceleration and what it means, it kind of helps if you think of the units this way. Right, our original way, as the slope of a velocity time graph, as the rate of change of velocity, right, and not centimeters per second squared or meters per second squared or miles per hour squared or something like that. So that reduces the units down here. Okay. Now, what's our x value? Well, x is what we graph on the horizontal axis, which is time, which is a t. And what's the y-intercept? Well, you probably got a pretty small y-intercept in graphical analysis. Does it make sense that there's a 0, 0 point? What would that physically tell us? It would tell us that when the time is 0, the velocity has to be 0. Makes sense with how we did the lab? Sure does, right? When on the frame, on the high-speed video that we analyzed, the frame where the wire was cut was where we put the 0 of the stopwatch, right, when you reset the stopwatch. And so we really did have a pretty good 0, 0 point here, which is why I told you to put it in the data table, right, and to put it in your graph, but logically makes sense, right? Which means that's it for the math model, right? You don't have to put a plus 0 on there. Interesting. So, what if we did the lab a little different? What if instead of doing what I just said, where we reset the stopwatch to 0 when the wire was cut, What if we cut the wire, went several, 10 frames, and then reset the stopwatch? You with me? So that means that 0 time occurred when the puck was already moving down the ramp. What, if anything, would that change on our velocity time graph? Would it change the slope? Remember, we just defined the slope as the acceleration, the rate of change of velocity. Does the puck speed up any faster if you started the stopwatch later? Well, no. I mean, in the video, right? The video is the video. It speeds up at a rate that it does in the video. It doesn't matter how you manipulate the stopwatch measuring tool in there. But something would change, right? At 0 time, would it have 0 velocity? No. Right? There would be a y-intercept. Parallel line, right? But same acceleration, but a different y-intercept. Which hopefully makes sense, because what would the y-intercept tell us in this case? It tells us the velocity at 0 time. What we are going to call v sub o, or the initial velocity. Graphically, this is the y-intercept of a graph of velocity versus time. Right? Physically, it is the starting velocity, right? The velocity it starts with at 0 time. You might remember we use the symbol x sub o to mean initial position. So this goes right along with this, right? V sub o is initial velocity. V will be final velocity. V sub o will be initial velocity, just like we did with x and x sub o. So given that, let's make a y equals mx plus b math model of this graph, right, which has a little more information than our previous one did. Our y variable is still what we're graphing on the y-axis, which is the velocity. That's going to equal the slope, but what did we just decide the slope actually tells us about the motion of the dry ice puck as it moves down the ramp? It tells us its acceleration. That's the final velocity, right? It tells us the acceleration. The x variable is time, and the y-intercept, we now know, is the initial velocity. Now, if you were to look this equation up in the book I never gave you, or if you went online maybe to the physics tutorial online book that I've shown you, right, this is the way you would see this equation, which is okay because after all, this is addition, and we do know that vector addition is commutative, isn't it? Right? We did that lab already. Vector addition is commutative, so I can flip the order. So this is traditionally the way it's written. The final velocity of the ice puck is equal to the initial velocity of the ice puck plus its acceleration times its time. That would allow us to know any 3 of these and calculate or predict a 4th. This is one of actually 4 equations we're going to have by the end of the unit. But we're going to spend some time doing some graphs, lots of graphs, some motion diagrams, and some other things before we get into some heavier math. Or we're going to do the math right on the graph so that we understand it. Okay. Now, this is a special kind of motion. Notice that our velocity time graph is linear. Well, what's true about the slope of a linear graph? It's constant. And what's the slope of a velocity time graph represent? The acceleration. So this is one-dimensional, uniformly accelerated motion. Uniform here in physics, generally, it means constant. I don't know why they don't use the word constant. They don't. They just call it uniform. Okay, so you will notice that the name of this particular model that we're building, right, the topic on Google Classroom is uniform acceleration, because that's what we're going to study in this unit. We're going to look at lots of different examples of things moving with a uniform acceleration, with a constant acceleration. Here's our first math model that will help us calculate things, but more importantly here is the graph. Now, this part's fun, okay? I want you to take out your lab sheet and your lab extension sheet. Take out both of them. If you want to, pause the video here and get them both out of your folder, okay? I want to compare the slopes of these two and see if we can get some meaning here, okay? In the lab extension, right, we graphed a velocity versus time graph. We got a slope of roughly 356 centimeters per second squared, and we decided that that was what? The acceleration. In our original lab, we linearized the position time top opening parabola by squaring it, squaring the time. So we had a position versus time squared graph, and we had a slope of around 178 centimeters per second squared. Is this the acceleration? It's got the same units, centimeters per second squared, but it's sure not the same number. Look at your numbers. What do you notice? What is true about the slope of your original lab linearized graph compared to our acceleration? It's exactly half the acceleration. Do you see that? It's kind of cool. Kind of an interesting thing to pop out of here, right? And this is an experimental result for the moment. We'll tack it theoretically in a moment here. But I want you to go back. I originally told you on the PostLab, all right, from the dry ice puck on the ramp lab, I said on the very last thing, which was making the math model, to write down slope equals and a little question mark, right? Because we didn't know what that slope meant. Well, now that you got your lab sheet out, go ahead and fill that blank in and say the slope is 1/2 the acceleration. Kind of hard to know then, right? But we know that now. This again is a hallmark of uniformly accelerated motion. Position is proportional to time squared. The velocity is proportional to the time. The slope of position times squared is 1/2 the acceleration. And this is certainly what we found experimentally. Did your numbers work out that way? I bet they did. If you were able to put your slopes into the Google Forms, yours is basically half as much, right? Now, we're about to do something that you may have never done in a science class up to this point. So we are going to do something called a proof, which is we're going to attack this theoretically with what we know about graphs, right, and what we know about math, and see what result we get for the relationship between position and time and all that stuff, okay? So, let's take our velocity time graph, and let's start with the simple one like we did in the lab, right, where we had 0 y-intercept, we had 0 initial velocity, right, and a linear graph. We can certainly make a math model out of this, right, y equals mx plus b, although, you know, the b is 0 in this case. So y is the velocity. The slope of a velocity time graph is the acceleration. The x variable is the time, and the y-intercept is 0. So the final velocity equals the acceleration times the time, only if we have a 0 initial velocity, right? But slope-intercepts are not the only things we look at on velocity time graphs. You might remember that during the constant velocity unit, we also examined the area under the curve of a velocity time graph. Let's do that now and see what it gives us. Let's allow, say, this dry ice puck moves for a time we shall generically call t, at which point it is moving at a velocity we shall call v. Then the area under the curve is simply a triangle. Anybody remember what the area under the curve of a velocity time graph represents? It tells us the object's displacement, change in position. And we don't need to use calculus. It's a calculus idea to find an area, but we don't need to use calculus because it's a simple enough shape, and we've done the lab, right? We know how to find the area of a triangle. It's simply 1/2 base times height. So the area of this graph is going to be the displacement. 1/2 the base is how long? It's just t, so 1/2 t, and the height is v. You see how I made that math model? I'm examining the area under the curve, which is the displacement, change in position, and that's 1/2 the time times the velocity, right? Base, height, 1/2. This may not look like much, but remember, the final velocity is also acceleration times time. So we ought to be able to plug that in right here to create a different math model. And I'm going to write out the displacement here, which is kind of traditional to do. So displacement is final minus initial position. So we have 1/2 times the time times the quantity acceleration times time. We'll multiply this all together. What's t times t? Oh, the initial position was also 0, right? That's where we put the edge of our ruler, hopefully. So we get 1/2, the final position is 1/2 at squared. Do you see it? Do you see it? What this predicts? This is predicting the relationship between position, acceleration, and time for the dry ice puck going down the hill, right? And this is only when the initial velocity is 0. I don't want you to memorize this equation. You'll notice I don't have it boxed in. All right, this isn't an equation you need to put on your card or something like that for a test. Right? Rather, we'll get a more complex version with a non-zero initial velocity way towards the end of the unit when we're doing a lot of the math. But I want you to compare here, right? These are the results of our lab, right? Just our lab. We had the position time graph. We found that we had to square the time, right? So position was proportional to time squared. And we created this math model from this graph, or something very near to it, depending on what your slope exactly was. We did that by doing y equals mx plus b, right, on this linear graph. But theoretically, we just created an equation that said the relationship between final position, acceleration, and time is this. Final position is 1/2 the acceleration times the time squared. Well, if our theory is really a good predictor of reality is our experimental results up here, right? Then these equations must match. And notice they do in some fundamental ways. Both of them have a y, which is the final position. Both of them have an x, which is the time squared. So both theoretically and experimentally, we have position proportional to time squared, right? We found that up here, or right here, experimentally. Theoretically, our equation is saying the same thing. We need to use time squared and position. All three have 0 y-intercepts. What does that mean? That means that our slope, for both of these equations, say it this way, for both of these equations to accurately model reality, our slope experimentally must be theoretically 1/2 of the acceleration. I know, that's a mind blower, isn't it? Right? Isn't that exactly what we just found experimentally? Right? We just looked at the numbers and saw that the numbers, the slopes, showed that, right? That the slope of this position time squared graph was actually 1/2 the acceleration, the slope of the velocity time graph. Theory matching experiment. This, folks, is science, and it's using the language of mathematics to describe what we are seeing in nature. Right? And if we understand the rules of math and the language of math, we can use it to more concisely model the world, right? Or what we see in the world. I know that's a very deep, deep thought here, right? But I mean, that's pretty mind-blowing when you look at it. And I said this might be the first time you ever did this because you haven't probably had enough math to do a lot of this up to this point, right? But this class is going to marry a lot of the math that you've done with reality and science. And physics, and especially mechanics, is a great, great tool to see that. In fact, in some districts, they do something called Physics First, where they actually teach this kind of stuff to freshmen while they're learning algebra. They're also learning physics, right? So that they can look at y equals mx plus b, but give it a context, right? A physical context. Well, we're doing it kind of separate, but still, you have gotten there now. Right? So take a moment and enjoy the depth of what we've done over the last few days here, right? In showing this experimental and theoretical result. And now, just for fun. A former student sent me this a couple of years ago, and I thought it was cool, funny, and I wanted it to be put into the PowerPoint. And so I put this into the PowerPoint. This is a video of noted astrophysicist Neil DeGrasse Tyson being interviewed by Katy Perry. Why? Who the heck knows? But he just literally blows her mind. So watch this for the end of the video.
So there were no science teachers or math teachers that had any influence on you?
No.
Positive or negative?
No, not in particular. I wasn't ever good at math. I was always promised no math. There will be no math on this show. So
Maybe by the end you'll be good at it.
I know. And then, is math related to science?
Math is the language of the universe.
Numbers.
If you want to go to China and speak to Chinese people, you learn Mandarin? Or,
Yeah.
Okay. Go to Spain, you learn Spanish?
Yeah.
Want to go to the universe, you learn math. It's that simple. I mean, it's that
I
straightforward.
know that people have done this before on your show, but I just want to go and do it once.
Yeah, so that's why math is so fundamental.
Right.
And it's kind of mysterious because we invented math out of our head, yet it applies across the universe and across time.
Right.
So it's completely amazing.
Amazing.
That this thing that came out of our head even works
Yeah.
to describe
Did
it.
we invent it, or
Yeah, we kind of invented it.
as a language?
Yeah, as a language to communicate with great precision what's going on in the natural world. So.
Wow.